Frank J. Tipler is a professor of mathematics and physics at Tulane University and a pioneering figure in the study of global general relativity. He is the co-author, along with John Barrow, of the definite scientific treatise, The Anthropic Cosmological Principle, which rigorously investigates the necessity physical constraint for the emergence of intelligent life. His expertise in the causal structure of space-time led to the discovery of Tipler cylinder, a celebrated exact solution to Einstein field equations that theoretically permits the existence of closed time-like curves, demonstrating that the laws of physics do not strictly forbid time travel. Renowned for pushing the logical limits of physical law, Tipler formulated the omega point theory, a provocative cosmological model that synthesizes thermodynamics, information theory, astrology. He argues that the known laws of physics requires the universe to evolve towards a state of infinite computational capacity, enabling the indefinite continuation of intelligence and the potential simulation of all past physical states. This work, often described as the physics of immortality, represents one of the most daring and mathematically rigorous attempts to deduce the ultimate destiny of consciousness from the fundamental axioms of the universe. So with this brief introduction, I would like to kindly invite Professor Frank J. Tipler to deliver his talk.
Okay, what I'm going to talk about really fits under the category of the final anthropic principle, and it fits in with what the previous speaker said. In the original formulation, it says, in any universe, intelligent life must come into existence and persist until the very end of time. I will reformulate it today in much more abstract terms. A universal computer, a computer, in other words, equivalent to a universal Turing machine, will, in the course of future history, be consulted. What I will shortly do is show that the laws of physics imply that such a computer will, in fact, be constructed. But why worry about the far future? We can't observe it. The reason in physics to worry about it is because requiring the consistency of the laws of physics in the far future constrain the universe now, which we can observe. Next slide, please. Historical fact. Physicists, even the great ones, typically reject the laws of physics when the laws of physics imply something they happen not to like. Example one, Einstein famously introduced the cosmological constant, the worst mistake of my life, he called it, to eliminate what his own equations implied, namely that the universe had to be expanding. Now, that discovery, the fact that the universe is expanding, was the greatest cosmological discovery in the first half of the 20th century. Second example, Steven Weinberg, in a historical diversion chapter of his book, The First 3 Minutes, wrote that he personally, Nobel Prize winning great physicist, rejected the laws of physics because they implied the existence of an early universe filled with a cosmic background radiation. The CBR, of course, was the second greatest cosmological discovery in the 20th century, the greatest cosmological discovery in the second half of the 20th century. Next slide. The great cosmologists, there are many here today, are repeating the mistake. They're rejecting the laws of physics. What are the laws of physics? My colleagues here, and again, they're great cosmologists all rejecting. First, the second law of thermodynamics. Second, quantum mechanics, specifically unitarity, the Bekenstein bound, otherwise known as the uncertainty principle, and wave packet spreading. They're also ignoring the standard model of particle physics, specifically the Higgs and SU2 left fields, general relativity, which implies the universe began in a singularity, and also spin 2 quantum gravity, otherwise known as the Feynman-Weinberg-DeWitt-Wheeler theory of quantum gravity, which also implies an initial singularity. Next slide. These laws of physics solve most, if not all, cosmological problems. Which problems? First, why is the universe homogeneous and isotropic. This follows, as I'll show, from the second law of thermodynamics and the Bekenstein bound, no fine-tuning of the inflaton field, or no inflaton field at all needed. Why is the universe flat? That comes from standard quantum gravity and old familiar wave packet spreading. Why do ultra-high energy cosmic rays exist? Now, these are extremely high energy protons coming in from intergalactic space, and they should not exist according to standard cosmological theory. But we've seen them for 60 years. Many groups have seen them. They are a real phenomena. Next, why is there only matter and no antimatter? Let's go back. Why did WMAP and the Planck observatories observe the Sanyayev-Zeldovich effect to be too low? It's the SU2 field. The ultra-high energy cosmic rays, it's the SU2 field. Why is there matter, only matter, and no antimatter? It's the SU2 field. What is the dark matter? And what is the dark energy? Dark matter, that's answered by the standard model Higgs field. Dark energy, it's the standard model vacuum. Next slide. Let's see how this works. First of all, we need to study what physics tells us about the far future. And we all know Hawking showed black hole evaporates. Now, he also showed that were a black hole to evaporate completely, the principle of unitarity would be violated. Now, black holes certainly exist. We've seen thousands of them. And were the universe to accelerate or even just expand forever, then all of these black holes we've seen would evaporate to completion, violating unitarity. But unitarity, which is a fundamental principle of quantum mechanics and implied by law of energy conservation, Susskind, University of Stanford University, showed that energy conservation violation by unitarity violation would amplify blowing up the planet Earth. Doesn't happen. Can't have unitarity violation. It can't be violated. So, conclusion, no black hole can evaporate to completion. According to general relativity, the only way this can happen is for the universe to come to an end before any black hole can completely evaporate. Again, according to general relativity, the only way the universe can come to an end is for the entire universe to end in a final singularity. Black hole singularities necessarily then are part of the final singularity. Okay, next slide. Now, Bekenstein showed that his bound implies that were there to be event horizons at the final singularity, the entropy of the universe would have to approach zero. But the second law of thermodynamics says the entropy of the universe cannot decrease, and the entropy of the universe today is currently far above zero. Thus, event horizons cannot exist. And this is a central statement of my omega point theory. Event horizons do not exist. That's why it's an omega point. It's a single point in the Penrose C-boundary construction. Now, a theorem of general relativity tells us further, this is the Sachs theorem, that if there were no event horizons, then the universe must be closed, mathematically, in mathematical language, spatially compact. Now, notice the important thing. The far future is now telling us what the universe must be like now. It has to be closed. Next slide. Now, let's consider what physics problems are actually solved in passing by having no event horizons. If there are no event horizons at all, in particular, there are no black hole event horizons, then, of course, information can get outside from the inside the black hole. Black hole information problem solved. Also, if there are no event horizons, then black hole firewall problem. That's a problem which people realized a few years ago that quantum field theory requires, if you have an event horizon just inside the black hole event horizon, quantum fields have to diverge in energy. that problem is solved. No event horizons. Now, remarkably, it's not generally realized that there are event horizons even in standard Minkowski space. But of course, they're not black hole event horizons, which come from trapped surfaces. And of course, there are no trapped surfaces in Minkowski space. Now, a careful analysis, which I've given in a paper, and I'll give it later if you want to read the details, these particular event horizons in Minkowski space cause a firewall problem, infinities, in standard quantum field theory, both those which can be renormalized away and those which call quantum field theory series, when you expand it in a power series of scatter the S matrix in a power series involving the coupling constants, to be asymptotic rather than converge. These infinities also disappear if there are no event horizons. Next slide, please. Now, what was the initial state of the universe? Once again, the standard model of particle physics and the Bekenstein bound give us the answer. Remember, Bekenstein showed if you approach a singularity, if you have horizons, then the entropy has to go to zero. In the early universe, we will have horizons, not event horizons. They'll call particle horizons. Particle horizons just time reversed event horizons. As you're going into the initial singularity, therefore the entropy of the universe has to be zero. The temperature also has to be zero. Now, zero entropy, what does that mean? It means the universe was in a unique state. The standard model tells us what that unique state is. It has to be a perfectly isotropic and homogeneous three-sphere. Now, remember, all we can deduce from the future, spatially, universe has to be compact. But now, the Bekenstein bound applied to the early universe tells us that compact space has to be a three-sphere. Filled entirely with one field, and the standard model picks it out. It's a self-adjoint SU2 left field. Such a field in an expanding universe will generate only matter, not antimatter. How this works, how this particular field will generate only matter, I refer you to Steve Weinberg's beautiful book, Quantum Theory of Fields. Next slide. If an XU2 field survived to the present day, it would constitute the cosmic background radiation. Now, two observations suggest that the background radiation is, in fact, primarily an SU2 left field. Remember what L means. It means the field couples to only left-handed quarks and leptons. Relativistic free electrons in galaxy clusters, that's what we're doing when we're measuring the SZ, Sonyaev-Zeldovich effect. The background radiation particles are coming through galactic clusters, and they're scattering off relativistic electrons in those clusters, and that gives rise to a temperature shift. That's the Sonyaev-Zeldovich effect. But if SU2 left is what is the primary makeup of the background radiation, these cosmic background particles would interact with only half of them, so the Sonyaev-Zeldovich effect would be half of what standard theory, assuming the CBR is all photons, would predict. And that is what WMAP and Planck actually saw when they observed the background radiation, looking at the SZ effect. Next slide, please. Now, more details of how the known physics solves this. All right, now let's solve the problems. Let's think about this. Dark matter, if the standard model is correct, then the standard model has to tell us what the dark matter and the dark energy are. Why? Because the standard model purports to be a theory of all forces and all particles except for gravity. Well, if there's dark matter around, there is, and there is dark energy around, there is, then the standard model must account for it, and it does. Now, what does it say? It says that the dark matter has to be an oscillation of the Higgs field. We know that a Higgs field, a scalar field, which satisfying the same equations to first order as the standard model, Higgs field, would produce a background field that is has its pressure zero. In other words, it is cold, dark, because the Higgs field would interact weakly and gravitationally with other matter. So that's exactly what we have. Now, in the process of creating the particles in the universe, the method is tunneling of the standard model vacuum, and that will have a back reaction effect on the vacuum. And it's been known for decades that the vacuum energy density is exactly a cosmological constant. So the creation of matter changes the cosmological constant, the standard model cosmological constant, from its actual value of zero to slightly positive. So we get the dark energy too. Now, why is the universe near flat? It's observed to be within experimental observations. The actual explanation is wave packet spreading. There's a theorem that if the universe is classical now, which it obviously is on the large scale, then its wave function must have been a delta function at the initial singularity, which incidentally shows the initial singularity must exist. You don't need fine tuning, because what happens if you have an initial delta function, wave packet spreading says it's going to explode outward. And each classical three-sphere universe then would be almost flat. You can look at the details in a paper, which I will reference in a... Here we are in my paper, Reports on Progress in Physics in 2005. Okay, now I've given some more details, particularly about the dark matter and the dark energy, in a more recent paper, the British Interplanetary Society Journal, in 2024, if you want the details of the mathematics. Next slide, please. Okay, let's now consider in more detail the ultra-high energy cosmic ray problem. All right, now what are they? They are protons with energies so large that they lose energy by pion creation whenever these protons clobber a CBR particle, whatever they are. Now, most of the cross-section for this particular process is due to a quark spin flip, which cannot occur if the background radiation is an SU2 left. Now, an ultra-high energy cosmic ray particle has a mean free path of only 3 megaparsecs, if the CBR is all photon, that's standard theory, but it has 450 megaparsecs, that's nearly half a gigaparsec, if the CBR is SU2 left. All the ultra-high energy cosmic rays would be coming from the Andromeda galaxy if the CBR were all photons, and that's grossly inconsistent with observation. I quote a most recent example of an ultra-high energy cosmic ray coming from apparently nowhere, the sun goddess particle, named after the Japanese sun goddess. It's coming from, this was reported in Science last year or so, coming from a void. There's nothing there. Now, my student, Daniel Piasecki, and I have been able to identify sources for all of the ultra-energy cosmic rays, assuming that the CBR is mainly SU2 left. People can't identify any sources for most of them if it's standard theory. The problem, ultra-energy cosmic rays, an anomaly for 60 years is now solved if the background radiation is SU2 left. Next slide, please. Now, let me emphasize, those who are ignorant of history are doomed to repeat it. Let me give you 2 examples from astronomy. John Couch Adams predicted the location of the planet Neptune long before Urban Le Verrier did, but Adams was unable to persuade any British observer to look for the planet. Now, historians have pointed out that he had telescopes in his possession which were perfectly capable of detecting Neptune. He should have looked for Neptune himself. Second example, Alpha and Herman predicted the background radiation in 1948, as we all know, but they were told by experts in microwave technology at Johns Hopkins Applied Physics Laboratory that it was impossible to find such an object. That's actually false. The Dickey interferometer, which had been made in the Second World War, Could have detected it, couldn't detect it in Boston, but if you tossed it in the trunk of your car, it was a really small instrument, drove to the top of Pikes Peak where there was no water vapor to speak of, you could have easily seen the CBR. Conclusion: Alpha and Herman should have done the experiment themselves. I have determined that I am not going to repeat past errors, so I decided I would directly test for the SU2 left CBR myself. Next slide, please. I persuaded the IT billionaire, Peter Thiel, to fund my experiment to directly test for the SU2 left nature of the CBR. Now, the way the experiment works in outline is this. If the background is indeed SU2 left and not photon, it would interact only, as I've mentioned before, with only left-handed electrons in a dielectric. Now, left-handed here refers to helicity, not the same as spin at non-relativistic energies, only at relativistic energies, and needless to say, we don't have relativistic electrons in a dielectric. But even CBR passing through a dielectric would interact not with 100% of the particles, but greater than 1/2, but less than 1. And thus, this would change the index of refraction as measured by the instrument if the CBR were SU2 left. It would be less than the photon refractive index, which we can look up and measure. Okay, so here's the basic idea. Send the CBR to a Fabry interferometer. That means you're measuring power of the background radiation or whatever radiation comes through at different frequencies, and you compare the CBR with an all-photon signal. Now, here are the results using the silicon. We use silicon as our dielectric because it has very little emissivity, so little background radiation coming from it, and a very high refractive index. Other materials can be used. Silicon is it's truth be known, it's the cheapest one we can find. We virtually got it for free. Next slide. Okay, let me show you the experimental apparatus. Most of this structure is just a screen to prevent background from the ground from coming in. And what you'll see in the very center of this picture is a little white circle. That's a plate holder for the silicon plates. Next slide. Now here's a more detail of the actual interferometer. You see the microwave horn, and you also see, this is at night because we do our observing at night, you also see the silicon plates in the holder right above the horn. Okay, that's the apparatus. Now, let's see what we should see. Next slide, please. Now, first of all, we made sure that we would have exactly what we should have if all photons were coming in. Now, the details of the interferometer, how the machine actually reacts to Planckian radiation at thermal equilibrium in the microwave. You have to check that. And the actual result, which we saw by putting EcoSorb on the silicon plates, is the very bottom. That's an experimental curve. And you see that it reproduces both of the possibilities of the other two, but it looks closer, the second one, than the top one. So we adjusted the interpretation of the data to the second one. Okay, what should we see if we are seeing background radiation, which is SU2 left, versus all photons? Next slide, please. This shows you the top one is the all photons, and the bottom one is, well, it's really a calculation based on SU2. That's assumed to be the background radiation. But we also know that the instrument will also see background radiation from the atmosphere. This is a standard fact about ground-based cosmic background radiation instruments. So what you see in the instrument is a superposition of the two. The end result is the bottom one is what you expect if you have the mixture of atmosphere and pure SU2 left. And the top one is the one what you would see if you have all photons for both. Of course, we have all photons from the atmosphere, but all photons from the background radiation. The crucial difference, I think it's obvious. You have the two peaks, but there's also a center peak. Now, let's see what we actually observe. Next slide, please. Okay, the top two are the top one, very top one, is all photons. The second one is background radiation, is SU2 left. And the very bottom one is what we see in the actual instrument. You see that small second peak. This data, 2016. Then we observed again. Next slide, please. Okay, once again, top is all photons, second, SU2 left, and the bottom one, there we see the middle peak again. All right, this is 2018. Okay, now, next slide, please. Another observation made in 2018. Again, top all photons, middle is SU2 left, and the bottom is what we see. Once again, we see that middle peak. Okay, next slide. All right, now here, once again, you're getting bored with this. 2019, we observed again, and there's that middle peak again. All right, so it's looking good for SU2 left. Okay, next slide, please. Okay, now in the previous ones, what we had was 3 plates of silicon. The only thing we could do is to vary the number of plates. All right, so the previous one was with 3 plates. Now we reduce the number of plates to 2 plates. Now, interestingly enough, in the 2-plate case, the calculations show that the 2 theories should be essentially to give the same result. The top one is all photons, the middle one is the SU2 left, and the bottom one is the observation. Lo and behold, it agrees with what we would expect from SU2 left, and of course, all photons in this case. Now, we have one other possibility of observations. We can observe through only 1 plate rather than 2 or 3. And the next one will show what we actually saw in that case. Next slide, please. Okay, 1 silicon plate. The top one, all photons. The middle one is the SU2 left field. You see, there is no peak at all in the middle of the graph, and there is 1 little peak for the SU2 left. And what do we see? That's the bottom one. There's that little peak sneaking in again. So, next slide, please. I think it's looking pretty good that the background radiation is SU2 left. But what I want is other observers. I hope to encourage, hopefully with this talk will help encourage other observers to actually repeat the observation. Because remember, you can't trust the result of an experiment until other people have confirmed it. So right now, here's the experiment. I have already published an outline with some of the details of exactly how the instrument was assembled in that Journal of the British Interplanetary Society. What I'm giving you today is all the data, and I think it looks much impressive data showing that the background radiation is SU2 left. Next slide, please. Okay, now I want to mention one other thing. We all know that the background radiation is Planck. This leads people to believe that the universe has to be in thermal equilibrium. And the reason people think that is of the Planck distribution. Remember what Peter Debye did? You're probably not aware of this, that he was the one who created this proof. You've all seen the proof. What you do is you extremize the entropy subject to energy conservation. That gives you the Planck distribution. The point is that that's not the only way a Planck distribution can appear. Planck didn't assume maximum entropy in his original derivation. Now, Stephen Hawking showed that a black hole will evaporate thermally. That is, the black hole radiation will look like a Planckian distribution with temperature defined by the mass of the hole sufficiently far away. But if you look at the derivation Hawking gave, he never once extremized the entropy. He got the Planck distribution purely from the Schwarzschild geometry. Now, in the case of the universe, remember I've already told you that the Bekenstein bound forces the universe to be homogeneous and isotropic, which is to say, Friedman. That forces the universe to have a Planck distribution. I've given the details of the calculation if you want to go through it. In my Reports on Progress in Physics paper in 2005, you can look it up. It's also on the archive. But the point is that seeing it's a Planck distribution is no indication that it's in thermal equilibrium. We know it can't be in thermal equilibrium early in the universe, at the very least. One of the Sakharov conditions is only if the universe is not in thermal equilibrium can we create more matter than antimatter, which is what we observe. So the claim is it's not in thermal equilibrium then, when matter was created. It certainly wasn't. And it's not in thermal equilibrium now. It has to be Planck. It is Planck. It's observed to be Planck to an extremely high degree of precision. But that high degree of precision is just measuring that the universe is homogeneous and isotropic to a high degree of precision. Now, let's follow through the final logic of what the universe must be like in the absence of event horizons. Okay, now it implies intelligent life will never die, which is the basic conclusion, the basic assumption, the final entropic principle. How do I get this? Well, how do you actually eliminate the event horizons? Now, the British mathematician Malcolm McCallum proved, in the 70s, that event horizons can disappear near the final singularity only if machine intelligence is present all the way into the final singularity, guiding the universe to eliminate event horizons. So, intelligent life has a glorious future ahead of it. Next slide, please. Okay. Now, eliminating event horizons requires our descendants, which will be artificial general intelligences, their computer power has to increase without limit. Now, there are some problems to overcome in order to increase the computer power without limit. Obviously, we have to turn off the current acceleration of the universe. The Standard Model actually tells us how to do this. Remember, the Standard Model is telling us that the acceleration is due to the vacuum tunneling, changing the vacuum because of quantum tunneling, generating the matter rather than the antimatter. So you reverse the process, you will turn off the acceleration. This allows intelligent life. In order to survive, they have to expand out and engulf and seize control of the entire universe in order to guide the universe into the final state. And to do this, they will have to cancel the acceleration on their good time. Effectively, what we will have is we will be approaching in the far future, before they collapse into the final singularity begins, an Einstein static universe phase in which intelligent life gets its act together, gains full control of the entire universe to guide it into the final singularity. Okay, so now remember, I emphasize again, unitarity, this fundamental principle of quantum mechanics, requires there to be some mechanism for turning off the dark energy. The Standard Model is the way it will, in fact, be turned off. Next slide, please. Okay, now the Bekenstein bound does something else interesting. It tells us that the complexity of a human being is limited. The complexity of the entire visible universe now is limited. All you need is a mere 10 to the 122 bits of information storage in order to perfectly emulate the entire visible universe. That's the Roger Penrose number. He got it right. The point is that if you have sufficient computer power, you can emulate the entire universe, and therefore, in the far future in which the universal Turing machine is being constructed, that is, Accessible memory is increasing entirely without limit. You will have plenty of computer power to emulate everything and everyone who has ever lived. Okay, so not only will life survive, individual human beings will be resurrected in the far future, never to die again. The laws of physics require it. If the laws of physics be for us, who can be against us? Thank you very much. Open to questions.
Yeah, yeah. Thank you, Professor, for your brilliant talk, and it was quite great. I would like to express my sincere gratitude to you for sharing your profound wisdom on both your theoretical and experimental aspect of your work. Thank you very much, sir. So we have got few questions. So yeah, so this is question by Bak, Bangalore University, India. He's asking Higgs fields has weak interaction with matter, but dark matter has no interaction with matter. Hence, how can dark matter be regarded as oscillations of the Higgs field?
No, you're not right there. Dark matter has no electromagnetic interactions with matter. Higgs field, I completely agree with you, has weak interactions, but the Higgs field has no electromagnetic interactions, has no charge. So it will look dark. That's what it's meant by dark matter. It's dark. Doesn't give off light, doesn't interact with regular matter to generate light.
Yeah, thank you, sir. Next question, please. So this is question by Ritvik. What is the quality factor of the FP resonance? And also there is a asymmetry and deep in the FP curves. What is the reason behind that?
I'm
2018
sorry, I
data, I
do
think.
not know what an FP curve is or FP
I
resonance.
think it's Fabry-Perot resonance, Fabry-Perot cavity, which you the curves which you saw, I think.
I'm sorry, I just don't understand the question.
Okay, next question, please. So this is question by Kumar Ravi from Swami Vivekananda University. Since both dark matter and dark energy are dark in the sense that they are indirectly inferred, would it be meaningful or even correct to interchange the terms dark matter and dark energy if the historical naming had been different? Or is there any fundamental principle of physics that prohibits such an
Well,
interchange?
the dark matter is called dark, and it's called matter. Remember, it's the standard model is lambda CDM. Lambda CDM is lambda refers to the dark energy, and CDM is cold dark matter. Cold because it has zero pressure insofar as anyone can measure it. Now, dark energy means that refers to lambda, the cosmological constant. That means it has plenty of pressure. So it has energy associated with it. That's why they call it energy. Dark because, once again, it does not interact electromagnetically with matter. So that is the reason for the origin of the terms, why physicists call it the dark energy, because it has pressure. It's dark because it doesn't interact with regular matter. Doesn't interact electromagnetically. And cold dark matter because it has zero pressure, looks just like matter, and that's exactly what the Higgs field looks like. Now, one of the slides apparently was not shown, in which I point out that this Higgs field oscillation looks like cold dark matter only if you include the lower order terms in the Higgs field. If you include all the terms, then there's a slight variation, which, depending on the details, which I can't measure, unfortunately, and can't calculate at the moment, may or may not be present. If they are present, what they would do is say that the cold dark matter is not really perfectly cold. It's slightly different from cold, and the end result is that it explains the Hubble tension. As you may know, the Hubble tension arises because if you measure the Hubble constant at the time of decoupling at redshift of 1,000, you get one answer. And you can, if you assume that the evolution of the universe from then to now is lambda CDM, that tells you what the Hubble constant is today. You can compare that with the measure you have today, an atom race. Johns Hopkins University Hubble Observatory says there's a discrepancy between the two. Now, Wendy Friedman in her lecture here says she can't confirm that, so it's an open question. But my point is, in the slide, which unfortunately was left out, is that the Higgs field as the dark matter can resolve that Hubble tension.
Yeah, thank you. Thank you very much, sir. So we will take a last question. So this question by Raj is, how would Higgs field oscillation dark matter manifest in cosmological data?
One of the ways, and I have a preprint, I haven't published this anywhere yet. The preprint just went up. Look at it. The Hubble tension problem, Hubble tension resolved by standard model of dark matter. One of the ways it would manifest itself is in the Hubble tension, again, assuming that's real. Another way, which I point out, is that you can actually confirm that this is the mechanism by looking very carefully at Higgs boson decays. Higgs boson decays will determine whether or not this explanation for the Hubble tension is correct or not. Again, that's in the technical paper, which is online.
Yeah, thank you. Thank you very much, sir. Thank you for addressing this question with so much depth. And on behalf of Bhaktivedanta Institute and all the audience, we would like to once again express our gratitude to you for joining us today and enlightening us with your words of wisdom. Thank you, sir.
My pleasure. Thanks for inviting me. Goodbye.
Thank you, sir.